So, hi everybody, welcome to my talk. I would like to tell you today how you can scale deep learning, so how you can do the distributed training for the huge data sets. And by saying huge, I mean data sets with a couple of millions of images, and how you can apply all this to the image recognition models. So let's start from the typical machine learning life cycle. So what we can see here, we are always starting with our raw data, and then we can do some sort of ETL process, calculate our features, and after we are ready with the features, we can train the model. And then if we are not really happy with our model, we can try to improve things, improve our metrics, so use hyperparameter search. And then after we are, let's say, have found the best architecture and the best hyperparameter combinations, we can put everything to production. And of course, our journey does not end here. We will have to monitor the performance of our model, and if something goes wrong, if the performance plunges, of course, we have to start the whole thing from the very beginning, maybe just retrain the data, retrain the model with the new data, maybe we will have to also change our pipelines. So let's see how we can apply all this to the image recognition models. So as a raw data, we have the images, and as a first step, we can maybe convert them, maybe resize them. Maybe if in our data set we have really different types of images, we can try to, let's say, build a one training set where all the images are looking like in the same time, in the same way, and then we can do the training. And yeah, when we have something to put into production, let's put it into production. And let's assume that we are doing all these things in cloud. So in this case, our images will be stored somewhere in S3 in the case of AWS, or maybe ADLS in the case of Asia. So we will need some sort of a distributed file system to access all these images. And then for the first ETL and conversion resizing part, we can use Spark. And then we can use actually any deep learning library out there. Today I will show all my examples based on TensorFlow and Keras, but you can use anything else as well, like PyTorch or MXNet. And if you would like to iterate faster, we will see how we can distribute our training process with the horovod. So let's get started with the preparing image data. So image recognition models are usually trained on GPUs, and the GPUs are still quite expensive. So it's really important to prepare our data pipeline in a way that it can feed enough image data to the GPUs. If our data pipeline is not performant enough, then the GPUs will not be utilized, and this just means that we are losing money. And Petastorm can help us here a lot. So it's a really nice open source library, was developed by Uber. And this library can help us closing the gap between TensorFlow or between, let's say, deep learning or Python world and big data world. Because what are we usually doing in big data? We are using Spark, maybe Flink, maybe something else, but at the end we are working with the big data formats like Parquet. So this should be some sort of a column-oriented format, and Parquet, I think, is the best alternative. And with the TensorFlow, usually we are working with NumPy arrays or HDF files. And Petastorm allows us to read this Parquet file that we can prepare with Spark, for example, and directly use them for training with TensorFlow or PyTorch or any other library. So let's take a look in a more detail how our pipeline will look like, and actually which pipelines are we going to have. So we're going to use Apache Spark for preparing our images, and then we will use Petastorm for saving them as a Parquet, and we will save it to some distributed file system. So I'm going to show all this on Databricks, so we will use Databricks Fuse file system, but it can be also HDFS in the case you're doing it on your own Hadoop cluster. And then we will have the training pipeline that can run on one node, or it can run on many nodes with GPUs. And we will use Petastorm for reading data, and then do the image transformation with the TensorFlow functions, and then we can actually do the training. By the way, the first pipeline, we don't need any GPUs there. We can utilize Spark, and we can have a lot of different machines. So we can scale it pretty good. And regarding the second training pipeline, yeah, like depending on the size of your data set, you can be good with one node, or we can try to speed things up and use a couple of nodes and use Horovod. So let me show you now a small demo how you can prepare the images with Spark. So here you can see my notebook. And so if we start working with Petastorm, the first thing we need to do, we have to specify the schema of the output data set, so our training set. And I will have here just two fields. It's going to be the image field, where the image as a NumPy array will be stored, and the label. And with label, I will have just a NumPy array with my labels. It's an easy one, right? Then we can read our images with the Spark. And for that, we can use image dataset from Spark. So we can do it in this way. And at the end, we will get the data frame. And you can see the schema of this image data frame. So we will have the path, we will have the binary image, and we have some metadata like, what do we have actually here? Yeah, we have number of channels, we have the modes that tell us what sort of image is it. Is it RGB, is it RGBA, is it just a grayscale? And yeah, height and width. So now we would like to convert our image. And we can use Spark UDF for that. So here is my image dataset, and then I'm applying my UDF. And here you can see the code of this UDF. So within this UDF, you can do anything you would like to. So actually UDF, it's Spark user-defined function. So here I have implemented it in Python. You can do it in any, let's say you can do it in Scala as well. And you can use this representation, so this binary representation that Spark gives you, or you can just read the image directly from the file system if you, let's say, for some reason would like to. So after that, I'm joining a couple of things. So doing the label processing. And yeah, now like we are ready with our images, with our training set. So we would like to store it to the file system, and at first we will have to use this materialize dataset method from the Petastorm, and then we can give our output path, and we can give our schema, and then after that we can use classical Spark API for storing this data. This concludes this first demo, and how you can use Petastorm with TensorFlow and Keras directly I will show you during my demo that will be a little bit later. So let's now discuss how we can, oh, sorry, let me enter the presentation mode. Yeah, so let's discuss how we can speed up the training. There are actually two most common approaches to distributed deep learning. It's model parallelism and the data parallelism. The model parallelism means that we cannot fit the model to one GPU, so we would like to split it up, and multiple GPUs will do the training at the same time. So it's quite complicated, and with the modern GPUs, we don't always, actually, almost always we don't need it. So we can stick up with data parallelism. And the constraint here is that our model it must be possible to train one model on one GPU. So what we are here actually doing, we are splitting our data into the chunks, and each training process will train own chunk of data, and then we have somehow to come up with the idea how we can average all the gradients. So because we will have a couple of, like, one model for a GPU, and then we have to somehow come up with one model and not with like so many of them. And one of the approaches for that is to use asynchronous parameter server. So how this is working, we have two types of nodes for working. We have parameter server nodes that contain the model weights, so our parameters, and we have the real worker nodes that are doing the actual training. Of course, the worker nodes are equipped with the GPUs. And the worker nodes, after they, let's say, they do the training steps, they send the gradients to parameter server, and then parameter server can update the model. If you have just one parameter server, it will become just from the very beginning a bottleneck. So companies like Google was using multiple parameter server, even lots of them. This, of course, is working, and actually the good thing about this approach is that our worker nodes, if they die, nothing happens. If we would like to add this, let's say we are training with 10 nodes, and we would like after that to add 5 more nodes, it's going to work. It's okay. But the problem is that if we have a lot of parameter servers, then it will be apparent that we are actually training on the stale parameters, and different workers can have different versions of the parameters, and of course all this really affects the metrics that we are after that will get. So the better approach that I think now most of the deep learning libraries are starting to adopt is called synchronous all-reduce architecture. So with this approach, we cannot add the nodes or remove the nodes during the training. And another requirement is that we have a really good network. Or that we just do the training on one node, but with with multiple GPUs. That's also a good option. And with this approach, we don't have parameter server. Every node has own version of the model, and after the training steps, they will exchange with the gradients, and then they will just average all the gradients. So I would like to introduce you Horowat library. That's the library that was developed by Uber, and it implements this all-reduce algorithm, actually the ring all-reduce. So here the workers build the ring topology, and they're just sending the gradients to the next worker, and exchanging the gradients just as a ring. And it's really easy to install it. At first, you can install any deep learning, so the deep learning library you're using, let's say TensorFlow or Keras, and after that you can install the Horowat with Conda or pip, and the Horowat will understand that what library are you actually going to use. And it was created with the following approach in mind, that you already have some let's say some pipeline that trains your model for one node, and it's quite easy with Horowat to adapt it for distributed training. So you can use your TensorFlow version. You don't have to, let's say, change a lot of things. You can just add things that are important for Horowat, and then your training pipeline will start being distributed. So let's discuss a little bit the architecture, how Horowat is working. So we can have multiple nodes. Each node can have multiple GPUs. So in our case, we have 2 nodes. Each of them has 3 GPUs. So it's just, let's say, for the sake of presentation, usually we have 4 GPUs or 8 or even 16. And we have this Horowat function that actually does the training, and Horowat will run this function on each node. Actually, it will run this function on each node for each GPU. So we will have, in our case, 6 Python processes that are running this function, and they will do the training. And we will just, after that, I will show you how you can add special callbacks that will average the weights during the training after each epoch. So how you can start using Horowat? At first, you have to import it and run the HVD init. So run the initialization function. Then we have to pin our current process via which is active now, to the GPU, because it will use this GPU for the whole training period. Then we have to wrap our standard optimizer that we are using, so it can be any compatible TensorFlow optimizer with the Horovod distributed one. And then we have to add a couple of callbacks. So why do we need these callbacks? At first, we have to make sure that all the these processes, all the worker processes have the same initial state of the model weights or parameters, and then we have to do the averaging of this model weights during the training. And here you can see how the whole function can look like. So we have our optimizer, we have the callbacks, and then we can just call standard keras model.fit method or .fit generator. So basically, we don't change anything, we just add a couple of calls to your existing code. And on Databricks, you can run the Horovod with Horovod runner, and then you can just pass the function parameter and number of parallel processes. Usually, it's a number of GPUs. Or in a case you're doing it with, let's say, Hadoop cluster, then you can use MPI run for that. So the question is, how does it actually scale, and how expensive it's going to be? So here are the results of one small test. So I have used DenseNet for this test with the data source with 110 images. That were grayscale images coming from the National Institute of Health, so chest X-ray images. And I have used 1, 2, 3, or 4 nodes, and each node was equipped with 4 GPUs. So like the first one, this means we are doing distributed training with 4 GPUs. 4 means that we have 4 nodes, 4 GPUs, each 16 GPUs. So as you see, it does not scale linear, but the scaling is quite good. So we have something about like 100 minutes for 4 GPUs, and for 16 GPUs we have something about 25 minutes. So I think it's not that bad. Now we know how we can prepare our images. We can do the training, do the distributed training. We can do it fast. The question is how we can improve our model. So how we can come up with a better, let's say, improve our accuracy or improve our metrics. So that's our pipeline. And the question is what exactly we would like to improve, what we would like to tune. Of course, the first answer would be we would like to tune just the training step, but I think it's not always the optimal answer. Actually, we have to tune the whole pipeline, because there are a lot of things that we can tune, let's say, during the image processing. We can try different image augmentation techniques. We can prepare our source data in maybe some different ways. We can build different features, and that can give us a lot of benefits. If we have a really big image dataset, we can actually also tune the whole architecture. Let's say we have the convolutional network, and we can tune different properties of the convolutional network. We can tune fully connected layers. Let's see, try different configurations. Of course, we can tune the probability that we have in dropouts. And if we would like to try with existing architecture like DenseNet or ResNet or exception, something else, we can try to even tune the number of dense blocks within the DenseNet. We can try to make our dense blocks maybe a little bit bigger or smaller, or try different configurations. And of course, we can try to different learning rates, try different optimizers, or try the real hyperparameter. And the interesting question is how we can organize all this. So by tuning, so tuning means that actually we will come up with some hyperparameter combination. We just run this, and after that maybe we run it a couple of times, and then we see how what are the results, and then we will come up with the better version of our hyperparameters. And this process will like iteratively be done a couple of times. So it's really important that we save everything that we are doing. So we save all these parameters that we are actually changing, that we save them somewhere, that we can after that track our experiments. And MLflow can help us here a lot. MLflow, it's another open source project, and it allows you to track everything that you're doing with your model. So you can track the parameters, you can track the metrics, and you can save the whole model with MLflow. That is MLflow tracking and MLflow models. MLflow supports saving, I think, most of the models coming from most of the well-known frameworks. There is a native support for TensorFlow, Keras, Escalon, also PyTorch, MXNet. And after that, after you track all this, you can search and see what you have tried and see what's working best, what's working not really good. So here you can see our pipeline, and we will have different ML flow. We will have different models that we will have for different runs, and then we have to come up with the best one, and we can organize all this as an MLflow experiment, and each our try will be stored in MLflow as the run, and we will have our parameters that we have tried, and we will have the metrics and the model itself. And after that, let's say when we find the best model we would like to deploy, we can use model registry to promote this model to the next stage. Let's see, say that this model is staging now, and after that maybe we can do a couple of more tests around it, and then we can even put it to production. So how we can do this tuning? Of course, we can do the manual search. We can use some easy algorithms like grid search or random search. Escalon can do this as well, and with Spark we can run random search or grid search in a distributed way. But the bad thing about it is, okay, it's not bad, but it's just not efficient, that both of them will search only the points or the combinations of hyperparameters that we are actually has defined. It will not come up with something completely new. And the population-based algorithms and Bayesian algorithms can evaluate, so like do a couple of tries and then use the optimization technique to narrow down our search and try really to try the combinations that maybe will bring us better results. And I'd like to show you how we can do the training, so the hyperparameter search or tuning with HyperOpt. By the way, anybody heard already about HyperOpt? No? Okay. So it's really nice open source library, and it uses Bayesian optimization. There are a couple of algorithms there that you can try. And the really nice thing about it is that you can run it in a distributed way. So you don't have to wait for like training 10, 20 models. You can like run all of them in parallel. And now I will show you a demo of Horovod and HyperOpt together with Peter Storm. So let's get started with this. So here I have a notebook with all the things. So at first I have to import a couple of packages that I'm going to use, and I have to set up MLflow experiment where I'm going to store all my tries, all my runs. And here I'm going to use DenseNet architecture. So I have here the DenseNet code. Why I'm not using the standard one that we have in Keras already? Because here I have made a small change, so I can define what dense net blocks I'm going to use and how big they should be. So if you go inside here, I have added a couple of more blocks, and I can define how big the blocks are. So I'm doing it. Wait. I'm doing it here. And here you can see my model, and yeah, I'm creating my custom dense net. And here there are a couple of other things that I'm going to tune in a little bit later. So this method gets the dictionary with all my parameters. And here, like, I'm going to tune the regularization parameters, and I'm going to tune dropout probabilities, how big are my fully connected layers, and of course the dense net configuration as well. Here I have a couple of TensorFlow functions that can do the image augmentation for me. As you remember, we have had image transformation 2 times, once in Spark, another one after reading data with Peterstorm. So that are the functions that I'm going to use for that. And here, so what I can do, I can flip the image or actually do the random flip. I can do maybe the random distortion, random crop. So there are a lot of nice things that can be done randomly during the training, and that can bring a lot for your model, because it will make your model generalize better, because your incoming data will be always a little bit different. And here you can see my train Horvath function. So as I have shown, I'm doing the initialization. Then I'm pinning my process to the GPU. And after that, I'm starting the MLflow run, and all the parameters that I'm using to MLflow. After that, I will be able to see what exactly I have run and what and the results. So then I'm creating my model using the function I have shown you before. I will use Adam optimizer, and then I'm wrapping it with the Horvath one. And then I have my standard callbacks. And I have a couple of other callbacks that actually are pretty important. So at first, if we see that our model, let's say the performance is not getting better, our model doesn't learn anything, so our metrics do not improve for some time, then this reduce learning rate on plateau callback can automatically reduce the learning rate. It can improve things. Not a lot, but we can get another couple of percentage points. Then we have the early stopping. We don't have to train our model forever. We can, if we see that it does not learn anything, then we should just stop it. Why wasting GPU resources? And then we are coming to the Peterstorm. So here is the code that you can use to read the dataset we have written before with Spark with Peterstorm. So we have here 2 calls. The first one is make batch reader, and then we are providing it with the path. And in the case we are using Horvath, we have to define a current shard and the number of shards we have. So shard is the worker process. So if we like have 16 GPUs, we'll have 16 shards. And then we can convert our TensorFlow, our reader to TensorFlow dataset, and that is a dataset compatible with TensorFlow, and then we can apply all these functions. Because they are standard TensorFlow functions, so we can apply them to this dataset. So that's what I'm doing here. And then we can pass this dataset to the Keras. for training. And then here I have my set of parameters, and I can just run it. So now let's see how we can run the hyperparameter search. So in order to do the hyperparameter search with hyperopt, actually for sklearn is working in the same way, we have to define the search space. So here I'm defining all the parameters I would like to try. So for example, at first I have some really easy parameters like learning rate and regularization things. Then I have parameters that are defining what image augmentation techniques I will use. So because of these probabilities, I will maybe get more data flipped and less data with change saturation. So for different models, it makes sense to, let's say, do the different, like try the different approaches. And then here I have my parameters that defining how my dense net will look like, and a couple of things for the fully connected layers and the dropouts. And then in order to run all this with hyperopt, we have to develop the hyperopt function. And here in this function, we can just run horovod, or if we don't want to use horovod in this case, we can actually run hyperopt in a distributed way and just have here standard Keras TensorFlow training. In this case, you will maybe have like 10 nodes. Each node will have one GPU, and each of them will just train our model, and then you can compare the results. Or you can run everything, like run hyperopt on the driver node and do the parallelization for each training process. And then, yeah, we can return the metric we would like to optimize. So I'm using error under the curve matrix. So actually, I would like to get the maximum value. So because of that, I have a minus here, because hyperopt will minimize everything. And then we can run it in this way. So I can show you how. Oh no, it's the wrong tab. Yeah, by the way, here are my notebook where I have created my performance comparison. So actually, I have done it with MLflow. So I have just run this training a couple of times, saved all this data to MLflow, and then with SQL query got the data from the MLflow, and then build this nice chart. But actually, I wanted to show you how you can after that see all your tries and all your runs in MLflow and how you can compare them. So in MLflow we have a really nice interface, so you can just take a look at everything that was done before. And we have here a couple of, so actually all the parameters we have used. And then we have the metrics. And we can take a look at the one particular run. And here we have also all the parameters that are corresponding to this run, and we have the metrics, so we can also take a look at the chart, how this metric was growing over the time. Steps. And we see that, yeah, the best value was 0.82, and then it's like almost stopped growing. So that was it. Any questions?